Okay, this week and next week, we're going to use 2 weeks to finish the next lecture, which is about image classification. But before I start today, I want to mention a little bit about your course project, because according to the syllabus, let me open it. Your course project proposal is due in, I think, 2 weeks, right? So this is this week, right? So next week and the week after next week. And it is week 11, right? On week 11, there will be an exam for what we have learned so far. I will make announcement about exam later. But in the same week, you are also going to submit your course project proposal. Okay, and about this proposal and what you need to do for this project, you can refer to these 2 documents, okay, to get information about what you should put in your proposal and what you should write and what you should do for your final project and project report. And this PDF file here is a file created by your TA to say help you collect remote sensing data, of course for free, using internet. You should go through it. And about the project itself, what I want you to do is using what you have learned from the lecture and from labs of this class, to address a real world problem. Okay, please don't make it complex. Okay, don't be too ambitious. This is just entering level remote sensing class. Make your course project straightforward. Don't make it complex. Just collect free data online and commonly use data. For example, Landsat data. Okay, could be ETM plus, um, could be TM data, but make it simple. What is simple and straightforward? For example, you have learned how to calculate NDVI, right? And you are also going to learn how to carry out image classification in the next 2 weeks. You have these techniques and you know how to carry out them within ERDAS. So how about say this? I want to address the change of land cover types within Columbus City in the last 20 years. So how to address that? There are different land cover types, right? For example, you want to address the change of vegetation in the last decade or 20 years. Of course, in order to do this, you can use NDVI to address the abundance of vegetation within this specific city, right? You can download an image of the city from 10 years ago, okay? Say, for example, an TM image covering Columbus City 10 years ago, and you can use that image to calculate NDVI for the area, of course, for all the pixels in the image, right? And then you can do the same thing for another image covering the same area, maybe last year or even this year, right? And you can say there must be some kind of change in terms of NDVI. You can compare 2 images, right? To in general tell us if the area of vegetated, if the size of a vegetated area increased or decreased, right? You would ask how to do that. How to calculate the size of vegetated areas. You can do this. Use a threshold to pick all those pixels occupied by vegetation. Okay, a threshold of NDVI. And then you can use ERDAS to find out the number of pixels who match the requirement of yours. That requirement is a specific threshold for NDVI, right? So you know the number of pixels and you know the spatial resolution of your image, right? So you can calculate the size of each pixel. Maybe it's 30 meter by 30 meter, right? But no matter what, it's just an example. And then you know the size of each pixel and you know the number of pixels. Multiply them, you have the size of vegetated area within Columbus City. right? So you can simply compare the size of vegetated area. And another topic could be, say, how did this city expand? Or how did this city grow in the last decade or 2 decades? You can do classification and find out urbanized areas. We call usually these areas, they are covered by impervious surfaces, right? Including asphalt, metal, glass, and maybe concrete, cement, right? Later, in the next 2 weeks, you will know how to do the classification. And after the classification, you can find all those pixels occupied by urbanized area or urbanized materials, right? And you can do the same thing to address that, or you can find out, you don't have to compare, right? You want to know the size of water body in Columbus or in another city. You can also do classification or other image enhancement method to find out all those pixels occupied by water body, by water. And yeah, that's just several examples. Okay, make it simple, make it straightforward. Try to review all your labs, lectures, and browse online, play with all those websites, data collecting websites included in this PDF. Play with them a little bit, and you should have some sparks in your mind. Okay, and choose a very simple topic and finish this project. Of course, during I mean, for the rest of the semester, for the next 2 weeks, you can ask questions about proposal. You can ask questions using emails, right? And you can contact me, you can contact your TA, right? And after that, when you're trying to actually finish your course project, you can still email us, ask questions, okay? So that's all I want to say about your course project proposal, okay, for now, because it's due in 2 weeks. You should begin to think about what you want to do with this project, okay? That's all I want to say. Okay, today we're going to talk about image classification. So lecture 8, like I mentioned, I'm going to use 2 weeks to finish it. Okay, so this is the content of the lecture. I'm going to introduce image classification as a remote sensing method first. So there will be an overview. Concept of image classification, there are different types of them. We can use different principles to categorize different image classification methods. Okay, and after that, more concepts we're going to use in the introduction of classification will be introduced first, and then a general procedure of image classification. Okay, and after that, in the second part of the lecture, I'm going to introduce supervised classification, then third part, unsupervised classification, and then a little bit about object-based classification. And eventually, usually after image classification, we need to do accuracy assessment to address how accurate this classification method is for a specific remote sensing image. Okay, let's get started with basic concepts. So what is image classification? It refers to a process of assigning pixels in an image to one of a number of classes. Okay, for example, these classes could be water, could be forest, could be urban. Okay, as a result of image classification, a thematic map is generated. So here is a figure showing you the change of remote sensing image before and after classification. So on the left side, we have the original remote sensing image, right? There are multiple bands and there are pixels. And usually the value for each pixel is for brightness value, for reflectance, or for other variables. It doesn't matter. And we're going to use this original remote sensing image to carry out classification. Okay, and after classification, each pixel will have a new value, but that variable is not brightness value, is not reflectance or anything else. It is a number for a specific class. For example, after classification, there will be 3 classes, and I'm going to use 1 to represent water, 2 to represent forest, 3 to represent urban. Of course, these numbers should be integers, okay? And what does it mean? It means that after the classification, if a pixel has a value of 1, then that pixel is water. If another pixel has a value of 3, then that pixel is classified as urban. And if the third pixel has a value of 2, it means that this classification method assigned forest to that pixel who has a value of 2. So this is classification. So after the classification, usually we have this image B here. We can see there are a lot of patches, not exactly the actual situation. I mean, some patches, they could be very small, could be very large. And the boundaries here, they're very smooth, not necessarily this way when you are actually doing a classification. But this is just an illustration to tell you that after the classification, pixels, they are assigned with different values, different integers to represent the land cover type or the class of a specific location. Okay, and each pixel will have a value. Each pixel will have a value, and that value is representing a specific land cover type. Okay, okay. So let's talk about different types of classification. There are different methods for classification, okay, image classification. We can categorize these methods into 2 categories, right? So we can call some of them supervised classification methods and some of them unsupervised classification methods, okay? So the difference between them is if you need training samples or training sites to carry out the classification. If you need to create training sites to finish the classification, then this method is called supervised classification. If you do not need any training sites to carry out the classification, then this method is called unsupervised classification. Okay, so for supervised classification, the identities and locations of classes are known a priori, okay, which means that you have some prior knowledge about this area covered by image. And the spectral characteristics of training sites are used to train the classification algorithm for eventual land cover mapping of the remainder of the image. What does it mean? It means that in order to carry out supervised classification, you need to have some knowledge about the area covered by this image, right? For example, you know at a specific location within the image, that pixel is vegetation and you are for sure for that, okay? And another pixel is water body and the third pixel is urban. And you must be very sure about the classes of these pixels. And you can collect these pixels that you are sure about and use them as training sites. What does it mean? It means that, okay, this is a pixel and I know it. It's a part of a forest because I live nearby. Okay, so you're sure about that pixel, right? And that pixel can be collected as a training site. And why do we need training site? Because you're going to tell computer, not computer, the software, classification software that, okay, now I'm giving a pixel and I can tell you that this pixel is covered by vegetation and please use the spectral characteristic of this pixel to identify other pixels covered also by vegetation. Okay, so you're actually training the algorithm or training the software using your knowledge. You tell them, okay, this pixel is class 1, that pixel is class 2, that pixel is class 3, and you should provide as more training sites to the as possible to the software and make sure they are accurate. So the software will be trained by these training sites, and the software, the algorithm is going to classify the whole image based on the training sites you just provided. This is just like providing some food, for the software. So the software eats it, and it knows the flavors of different types of food, right? And after that, you provide even more food and cover its eyes and let it tell which food is which food. Okay, it's just like the GCP we use in geometric correction, okay? Ground control points, right? Similar to that. And we also have unsupervised classification methods. The identities of classes are not generally known a priori, okay? Computer groups pixels with similar spectral characteristics into unique clusters according to some statistically determined criteria. The analyst then relabels and combines the spectral clusters into information classes. What does it mean? It means that for unsupervised classification methods, we do not provide training sites. We would just let the software, the algorithm, to decide which pixels should be class 1, which other pixels should be class 2, and do this again and again. And eventually, if you say require 5 classes, the software will give you 5 classes. But the software, the algorithm doesn't know which is which. There are 5 classes, class 1, class 2, class 3, class 4, class 5. But which one is vegetation? Which one is water? Which one is urban? The software doesn't know that because you did not provide any training sites or knowledge. That's the reason why after unsupervised classification, you, the analyst, you need to relabel and combine the spectral clusters into information classes. You will decide the land cover type or the actual class name for class 1 and do the same thing for all classes. And sometimes you may need to combine 2 classes because sometimes it's not necessary to have too many classes. For example, after an unsupervised classification, a computer gave you, say, 3 classes. And after checking these 3 classes, you found out that class 1 and class 2, they are both vegetation, but class 1 is for trees, class 2 is for grass. Of course, if you need a very detailed information, you should keep these 2 classes separated from each other because eventually, after all, class 1 is tree, class 2 is grass. They are different. But if that is not necessary, if you only want to know if that pixel is vegetation, it's not necessary to have 2 classes, right? You can just combine class 1 and class 2 and name them as class 1. And it is not tree or grass, it is vegetation. Okay, so supervised classification, unsupervised classification. The difference is if you need to collect training sites, if you need prior knowledge to train your software, to train your algorithm, okay? Okay, and there is another method to categorize different classification methods, and it's called hard classification versus fuzzy classification. Okay, so supervised and unsupervised classification algorithm typically use hard classification logic to produce a classification map that consists of hard discrete categories. What does it mean? It means that after a hard classification, each pixel has a fixed settled value. For example, pixel 1, class 2. Class 2 is vegetation. Then it means that for 100% probability, this pixel is what? Is class 2. No matter what that class is, vegetation, water body, doesn't matter. So after a hard classification, you will have a final classification map consisting of M classes. Okay, M could be 1, could be 2, could be 3, yeah, usually user defined. But each pixel has a very, not very sure, each one has a settled fixed value for a specific class. Forest, agriculture, body, that's it. It's for sure. But what is fuzzy classification? Conversely, it is also possible to use fuzzy set classification logic, which takes into account the heterogeneous and imprecise nature of the real world. It means that what? It means that, okay, how do you know a specific pixel is 100% vegetation? Is it possible that within this pixel, there are some vegetation and there are some urbanized material, and there are also some water body? It's possible, right? Especially when the spatial resolution of your image is very low. Say for each pixel, it covers a 1 kilometer by 1 kilometer area in the real world. It's not likely that in the real world, an area of 1 kilometer by 1 kilometer is fully covered by a single land cover. It's possible, but not very likely, right? So it's more likely that within each pixel, the land cover type is very complex. There are multiple land cover types. So this is what we do. We do fuzzy membership grades. What does it mean? It means that, okay, for after the classification, okay, still we want to have M classes, and each pixel has a membership grade for each class. And this membership grade is usually from 0 to 1. And the meaning, you can consider this value as the probability of a pixel to be that class. So for example, a pixel has a membership grade of 0.5 for class 1, which is vegetation. It means that, okay, 50%, you can consider it this way, but different people, they have different thoughts. But say if this is 0.5, you can consider that there is a 0.5 probability that this pixel is what? Is fully occupied by class 1, which is vegetation. And of course, each pixel, we have M values. If 0.5 is the value for class 1, maybe 0.2 is the value for class 2. 0.1, maybe that's the membership grade for the same pixel, but for class 3. So it means that for each pixel, we do not have a single integer like the result of hard classification to indicate the specific land cover type of that pixel. For each pixel, instead, in fuzzy classification, we assign it multiple membership grades. The higher the value of membership of a membership grade, you can consider the more probability that this pixel belongs to a specific class. Okay, hard and fuzzy classification. And then we have per pixel classification versus object-based classification. Okay, so in the past, most digital image classification was based on processing the entire scene pixel by pixel. This is commonly referred as per pixel classification. all I have mentioned before since the beginning of the class, all those examples, they were per pixel classification. Why? Because like I said, each pixel should have a value or multiple values if it is what? Fuzzy classification to address the land cover type or the class of that pixel. So classification methods, they are usually carried out pixel by pixel. Okay, but more recently, object-based classification techniques have been developed that allowed analysts to decompose the scene into many relative homogeneous image objects, patches or segments, using an image segment process. Okay, the various statistical characteristics of those homogeneous image objects in the scene are then subjected to traditional statistical or fuzzy logic classification. What does it mean? It means that sometimes we don't have to do pixel by pixel classification. For example, when you're looking at an image mostly occupied by a huge lake, with some very fundamental knowledge, you know that, okay, this huge patch in the center of this image is that lake, is water body. You're pretty sure for that, for most pixels in this lake. Maybe for those pixels along the boundary of the lake, for those pixels, you're not sure if those pixels are water or land, but for most pixels of the lake, you're pretty sure it's water. Then why do you need to just classify all the pixels in this lake? So now, following the logic of object-based classification, we would just consider this huge area of lake as an object. And maybe on the left side of the lake, there is a city. Then we can just draw a general boundary for that city and form another patch. That patch is considered another object, it's city. So now we have two objects, object one, lake, object two, city. Maybe on the right side of the lake, there is farmland, so agriculture. Then we can use another boundary to create the third object, which is what? Agriculture land. And when we do classification again, we actually are trying to find out the land cover type for these three objects instead of a lot of pixels. Okay, so these objects, how do you find these objects? So they within each object or within each patch, you should be sure that each patch is occupied, is full of homogeneous what? Pixels, which means that water is very suitable for establishing or forming an object because water pixels, they are easy to recognize. It's not likely to make mistakes, to make a big mistake finding out areas occupied by water. So it's easy to find out a patch with homogeneous water pixels inside. But for urban, for agriculture, it's relatively more difficult to do that because within urban areas, there are different materials and even some part of the city is occupied by water, like a river. So finding objects for water, creating an object for water body is relatively easy, okay? But creating objects for urban areas may be the most difficult job if you are trying to do object classification. And actually, agricultural land is relatively easier than the urban area because usually agricultural land is covered by vegetation or soil. Okay, but yeah, that's more details. That's another story. But here you just need to know that there are two types of classification methods, and we can use a pixel, okay, as a principle. If your classification method is carried out pixel by pixel, then it's per pixel classification. And if you're trying to just create objects based on pixels, based on multiple pixels. And when you're doing the classification, you are actually classifying objects instead of single pixels. Then this method is called object-based classification method. Okay. Okay, let's continue. And we also have image space classification and feature space classification. So this is about the method, more like the method for visualization. Usually when we are finishing, when we have finished the classification method, and we usually have multiple, we usually have one image. We usually have one image for the area covered by this image, okay? And it's based on multiple images because when we're trying to do classification, multiple bands are employed to address the spectral characteristics of each pixel to finish the classification. Okay. So this is image space. We use multiple images and we can see them here. Okay. And each image is for a specific band. And if we don't use this method, we can also just draw all those pixels within a multi-dimensional space. For example, here, we have 3 bands and 3 images. We can also address these 3 bands using 3 axes, right? This axis here is for band 1, this axis here is for band 2, another axis here is for band 3. So this is a 3-dimensional space. And for each pixel, it has 3 values, right? And the 3 values, they are for band 1, band 2, and band 3. Using these 3 values, we can locate this pixel within this 3D space. And if we do this for all pixels within this image, we can have this pixel cloud. We can have this pixel cloud. And we can use this feature space. It's not a real space. This space is established on the information of 3 bands, and each band can be considered as a feature axis, right? So we can use this cloud to finish the classification instead of using actual images. Okay, so what is the concept of image space and the concept of feature space? So this is a comparison. If in future, when we're talking about image space and classification, it means that we use actual multiple images, okay, to do the classification. And within each image, we have row number and column number for pixels, right? So I and J. But when we're talking about feature space, this space must be formed by multiple bands, and each pixel can be projected into this multi-dimensional space using its own values on all those bands and find a location within this space. And if you locate all pixels in this image, should have a cloud like this. And you can use this cloud to do the classification. For example, these pixels, let me use a pen here. These pixels, they're clustering at a corner of this cloud, which means they have similar values for band 1, band 2, and band 3. That's why they are closer to each other. Maybe they belong to the same class. Does that make sense? Of course. How about these pixels? They're clustering at another corner of this cloud, which means they are similar to each other in terms of their values on band 1, band 2, and band 3. So there are spatial clusterings here. And here is another corner of the cloud, right? Why are some pixels clustering nearby? I mean, very close to a corner of the cloud, because they're similar to each other in terms of the values on these 3 bands. So you can use this feature space to just find out pixels who have similar features, spectral features, and use this to do the classification. Okay. Okay, I will just stop here and I will continue in the next video. Thank you.